Hello. Thank you for coming. My name is Ted Moore. This is my colleague, James Bradbury. We're visiting here from University of Huddersfield in the UK, and we're going to talk to you about the FluCoMa Project that we are both postdocs working on. I'm going to talk the first half of the presentation, then I'm going to hand it over to James to do some more discussion. We have some other colleagues on the project, Owen Green, who is in Edinburgh, and Pierre-Alexandre Tremble, who lives in Huddersfield. He's the primary investigator on the project. And Gerard Roma, who used to be part of MTG, I just learned, isn't on the project anymore, but contributed huge amounts to the code base and the algorithms for FluCoMa. So a ton of the work is very much thanks to him. So FluCoMa is an acronym for Fluid Corpus Manipulation. The project is the sort of tagline we give it is it's a toolbox for programmatic data mining of sound banks, which we'll sort of unpack what that all means throughout the presentation. What we're doing is we're integrating machine listening and machine learning tools and algorithms inside of Max, SuperCollider, and Pure Data, so across all of the major creative coding environments used by electronic musicians. Just giving people tools isn't enough, so we're also making sure to provide lots of learning resources so that these musicians who are coming to data science and machine learning, maybe don't have training in that area, can learn about these things and learn about how they might apply these algorithms to their creative practices. So we have a website, learn.flucoma.org, that is still being populated, so it's about 60–70% of the way fully completed. Where we're putting up learning resources, tutorials, overviews, references, all this sort of information. We're also building a community around the use of FluCoMa, and we have a discourse page, which is an online discussion forum where people are asking questions and sharing code and having conversation about the tools. And also, this is a European Research Council grant. That's a 5-year project. And right now we're in the middle of year 5, so we actually complete the project at the end of August. We'll be making sure to wrap up shop then. So a little bit about how we're envisioning FluCoMa fit inside of the ecosystem of electronic music. There are a lot of tools that do similar things already. You're probably familiar with CatArt, a great program called AudioStellar, Wekinator, Rebecca Febrink's wonderful sort of neural network machine learning package. And then over in Python land, there's sklearn for machine learning and data science, Timbre Toolbox and Essentia for more musical-related applications. And then, of course, we have Max, SuperCollider, and Pure Data, the creative coding environments of choice for most of our user base. And we know that a lot of users are already sort of moving between these different things, right? Doing some analysis in Python, maybe taking that analysis and doing some synthesis in Max based on that analysis, maybe bouncing over to Wekinator to do some machine learning. Right, and so we're thinking that we want FluCoMa to fit in the middle of all of these, take some elements from each of them and house them in one toolkit so that you can do all of this sort of stuff with the same sort of syntax, same sort of pipeline of data management, being in one coding language for the whole of it. And also we want FluCoMa to not sort of be replacements of these, but be sort of embedded in the ecosystem as well. So if people still want to do their Wekinator, or people still want to do analysis with Essentia, that FluCoMa can easily, combine with those and just be part of the ecosystem, not a replacement for it. Another set of ideas that are sort of guiding our project is, as I was saying, we want these to be extensions, not replacements. So we're not going to replace Essentia or Wekinator. We're just going to add something to the possible tools one can use. We also have started using as a motto artifacts as ear training, by which we mean, for a company like Isotope, for example, they're making algorithms that do very complicated DSP. And because we're paying those companies a lot of money, they tune those parameters so that the output of their algorithm sounds really good every time. Right? That's sort of what we pay them for. FluCoMa is exposing all of these parameters to the user so that the user can tweak every aspect of the algorithm, which means that the user might have some artifacts that don't sound as good as, or just sound different than, what Isotope might supply. And we want those artifacts to be ear training. So hearing those artifacts and understanding how the parameters create those artifacts is a way of having our users actually understand the toolkit better, understand the algorithms better. So we want those artifacts to be a source of training for our users. And then also a philosophy of technology for all, that we think we want to invite everybody to this party. There's no entry level that we're going to turn people away from. We may orient people towards some other resources first if we don't supply those resources, but having FluCoMa be part of their process is definitely something we're interested in. A few mottos that we use. Musicking is humaning. So if you are a human, you make music, or you are a musical being. Imperfection is material. Again, this idea of artifacts. James and I, you'll hear, are sort of glitch musicians. We're interested in those artifacts and sort of the deviations from the normal as artistic objects that we want to use. Hearing is practice. Being able to hear the algorithms and how they unfold and what they do is important in the training of using these algorithms and these tools. And interface is identity, which is perhaps the biggest takeaway from the first 4 years of the project, that the way that you package and provide as an interface to users is probably the most important and most complicated question. You know, the algorithms, they do what they do. How non-negative matrix factorization works is something that has been established, and it's been used for music, and we are providing that algorithm to users. The biggest question for us is, how do we provide that algorithm to users in a way that makes it feel useful, artistic, expressive, approachable, learnable? That's really the task that we're trying to unpack. One more idea here is that we are often confronted with a continuum that sort of goes from one end, like Francis Domont, who's doing incredible work in the DAW, just organizing sound in a timeline. And the other end, we have somebody like Miller Puckett, who's creating a new environment, right? Is building pure data and has been for many years. And oftentimes, this is presented as a continuum from one place to another, with various steps in between. You know, maybe extending an environment, using things at a high level, and there's sort of this directionality that gets assumed, that you start here, and through practice and time, you work your way over to the more advanced technical application. And we are not looking at FluCoMa or as art making in general as the case this way. We're realizing that people are often moving back and forth between these things, right? Using an environment at a high level, and then popping over here and extending the environment for a little bit to have it do something that it couldn't do before, and then coming back and just using the environment, right? Or extending the environment in some way, and then coming all the way back here, because really when I'm being creative and composing, like what I'm doing down in the studio this week, is I'm staying mostly in the DAW, right? I'm just focusing on doing my work right here. So we're not thinking about this set of activities as a continuum of ability, but more about disposition. Like, what is it that the user is doing at any given point in time? How can we allow them to sort of be in different places on this continuum at different points in time according to the creative need that they're experiencing, rather than trying to frame our tools as some sort of linear progression. And right now, the driving question that we're asking, this year in particular, is in this activity of art making, which involves, you know, making sense of some sound and material, and then doing some stuff with some sound and material. The artistic practice sort of has this flow of moving back and forth between them, right? This is just the creative process, having some material, figuring out what to do with it, and then doing it, figuring out what that material means, and doing more. The question we're asking our users is, why might we place machine listening and machine learning? So why might we place a machine inside of this loop? And if so, where do we place it and how do we place it? And so this last year, we've been traveling around the world, doing workshops, teaching people FluCoMa, building the community on the discourse, and this is sort of what we're most interested in finding out, is how are people really interested in applying these tools, right? We have ideas about what we think people might want to do, but of course that isn't always what people end up doing, so that's what we're trying to figure out now, is what are our users actually doing with the toolkit? So this is a big list of some of the algorithms and tools that are in FluCoMa. I put it up here sort of as a teaser or something. If there are any questions or anything catches one's eye, we could talk more about it. But I'll actually draw your attention to the headers here. So the main parts of the toolkit are, it has algorithms for slicing audio, in intelligent ways, based on amplitude, based on transients, or based on something like novelty, looking through a sound file and analyzing it and finding where there is novelty, where a change happens, slicing that way. There's algorithms for decomposing audio, so doing harmonic percussive source separation, doing non-negative matrix factorization, modeling audio as sine waves, different ways of breaking apart the spectral content of a signal. We have tools for analyzing audio, things like pitch and loudness, as one might expect, but also some more spectral-based analyses like spectral flatness, chromogram, spectral centroid, MFCCs, or Mel frequency Kepler coefficients, which we find ourselves using quite a lot in the FluCoMa Toolkit. We have algorithms for transforming audio, doing things with non-negative matrix factorization again, or an algorithm called audio transport, which is a sort of unique spectral interpolating algorithm. And then over here on the right, we have what is probably the most salient addition to these creative coding environments, Max, SuperCollider, and Pure Data, are the tools for doing the data analysis. So actually doing sort of data science and machine learning inside of these creative coding environments with things like data sets, scalars, normalization, standardization, dimensionality, reduction algorithms, principal component analysis, nearest neighbor lookup, clustering, unsupervised learning, all of this stuff that you can do in the FluCoMa Toolkit. So next I'm going to talk about two pieces of art that I made using the project and sort of unpack how I did that a little bit. Before we move on to that, are there any questions about FluCoMa that anybody has?
So what there's any, some of these things are directly implemented in FluCoMa, or you use external libraries to do that?
This is all directly implemented in FluCoMa with code that is specifically written for FluCoMa. So it's not even sort of binding in different ways.
But what you mentioned about the integration with other tools, is that at another level, or also like here you can...
So the integration with other tools, one way is that we just want to make sure we're communicating that we don't think this is a replacement. We want it to be part of an ecosystem. Also, all of the data objects and information all exports and imports as JSON files. So one can easily, reorganize the JSON file to be loaded in a different environment or loaded into FluCoMa. And so, before I started using FluCoMa, I was doing some training I was doing some work in sklearn using the neural networks there. Once FluCoMa came around, I actually wrote a little script that just takes my sklearn neural network and writes it as a JSON file that can then be loaded into FluCoMa. And I have been using that same model now in FluCoMa, even though it was trained in sklearn. So that's the sort of idea, the relationship to the other packages, toolkits. Other questions?
And then this is accessible through Max, SuperCollider,
yeah.
PD.
Yes, and we've taken a lot of care to make sure that there's parity across all the creative coding environments so that on the discourse, on the forum, the online forum, for example, if people are communicating about what they're doing with FluCoMa, whether you're using SuperCollider or Max or Pure Data actually won't matter because the syntax is the same, the objects are named the same, the interface is the same. It's all, I did this with this object on this sound, and a user could easily go to their own creative coding environment and implement that. So, and that's important to us for building community and sharing ideas across the whole toolkit. So I'm going to share with you two pieces of music that I made using FluCoMa. The first one, just excerpts really. The first one is called Feed. And for this one, I'm using a neural network to do real-time audio classification of timbres. And the sort of subtitle of it is that I needed to train the machine to hear the way that I was hearing music and not the way that it was hearing music. So the initial creation of this piece involved what I call just the machine listening system. I had live sound input. It was actually a no input mixer that I was performing. the sound was coming into my computer. It was doing some audio analysis, brightness, pitch, loudness, etc. And then I was taking these audio analyses with onset detection and driving some lighting control of DMX lights, so theatrical lights. Basically just mapping the parameters from the analysis to the light parameters and then playing the lights, right? We'll see an excerpt of this in a moment. And after a few performances, I started to ask myself, are the changes that I'm hearing in the sound, right, the no input mixer switching between these different timbres, are those changes actually being perceived as changes in the lights, right? Is the audio-visual connection that I was trying to achieve with this, right, was I achieving that? And after a few performances, I decided that it wasn't as compelling as I thought it would be. The lights, when the sound changed, the lights changed, but was it really what I intended? So I amended this system to create a machine learning system where I essentially just inserted a neural network in the middle of the system here, which I had trained to identify the sonic changes as I heard them. So I trained the neural network to do classification according to the different timbres that the neural network, or that the no input mixer made. And we'll hear those timbres in a moment. So now what's happening is the live audio analysis gets classified as one of 4 different timbres. That classification gets sent to my lighting control system along with the parameters so that it's still using these parameters to control the lights, but also this added piece of information is helping strengthen the connection between the sound and the lights, being which timbre is it recognizing. So that now when there are fast changes between timbres, there can be really fast and distinct changes between lighting parameters. Here are the 4 sounds that I trained the neural network to classify. This is all no input mixer sounds. I think it's too quiet. It's in there. It's a quiet, sustained noise sound. And now we'll see some excerpts. So first, I'll warn you that there will be flashing lights, so if you're sensitive to that. So this first one is without the neural network, so just the raw parameter mapping from the audio analysis to the lights. And then we'll see an excerpt with the neural network added in, where the neural network is doing the classification in real time. Now here are 2 excerpts of a performance that has the neural network doing the classification. And here's an excerpt coming up from the same section that we saw previous in the other performance. There's a quote of Rebecca Feebrink, who's the creator of Wekinator. It also has done a ton of thinking and writing and research on like machine learning for creative practices. Yeah, really wonderful work. That I think is just so excellent in how it describes how myself and also our users are doing this stuff and what's really powerful about it. So I put it in here in its entirety, which is that there are certain things that we care about as musicians, for example, that are really hard to articulate in code. It's hard for me to talk about what kind of quality of sound I want and then translate that into a set of filter coefficients. It's hard for me to talk about how I want a performer to move on stage and then translate that into some sort of mathematical equation for their trajectory. But it's a lot easier for me to either find examples of sounds that have a particular quality or to give examples of movements, or if I'm using other types of modalities, often curating or creating examples are just way easier for us as people. And this relates to the types of tacit knowledge and embodied knowledge we bring to creative practices, which I love because I think it really encapsulates the power of this and also perfectly describes the issue that I was having, right? That I had this timbre that I wanted the lights to reflect, this sonic activity that I wanted the lights to reflect, and I couldn't get them to do that until I simply gave the machine examples of the sounds that I wanted it to know about. And then I immediately had a much more compelling audiovisual relationship. The second piece that I'm going to talk about, I cranked this, yeah, okay. The second piece that I'm going to talk about is called Quartet. And in this piece, I'm using audio analysis, dimensionality reduction, and of course, composition. So the artistic hypothesis that I set out when I created this piece was I wanted to use programmatic data mining, so the FluCoMa Toolkit, to reorganize a corpus of sounds according to their similarity. That was my artistic premise. This is the sort of workflow that I'm going to unpack for you. And in order to select what my corpus would be, I was asked to compose a work for the Switch Ensemble, which you see here. They're an instrumental ensemble based in New York. And so I wrote about 2 minutes of music for them. It was for flute, percussion, piano, and cello. And this was a remote collaboration, so I sent them this audio, or this score, and then they sent me back audio and video recordings of them each individually recording their part on a click track, so that it would align later. So now I had many, many minutes of recorded audio of this music that I had composed. In order to break this audio apart, I didn't do anything clever. The FluCoMa Toolkit, as I was saying, has intelligent ways of analyzing the audio and finding onsets or novelty. All I did was I took all this audio and divided it into slices that were 100 milliseconds each. So now we just had many thousands of sound slices that were all 100 milliseconds long. Then I analyzed all of these sound slices using a lot of analyses from the FluCoMa Toolkit. You can't really see the tiny text there, but I used things like spectral centroid, pitch, loudness, mellow frequency Kupfer coefficients, chroma. I basically sort of threw everything at it to get a ton of values that would describe each one of these sound slices in some way. This was too much data for me to really be creative with or even know how to approach, so I started using dimensionality reduction algorithms to try to extract the salient data or the meaningful analyses from these sound slices. So first I used principal component analysis, which was able to analyze my data set and reduce the number of dimensions from many, many dozens or hundreds down to just 11 dimensions. And these 11 dimensions don't reflect, they're not dimensions from the original data, but they are just dimensions that are combinations of other dimensions so that they give me sort of the differences between the data points. It reveals to me how I can recognize what sound slices are similar to and different from other sound slices. Here we're looking at it in just 2 dimensions because it's a screen, but each one of these sound slices now actually has 11 values that describe it in some way. So after finding these 11 dimensions using principal component analysis, I wanted to find a path through this 11-dimensional space that would visit each one of these sound slices just one time and make this path as short of a distance as possible. So this is the same as the traveling salesperson problem from computer science, in which a traveling salesperson is visiting different cities and wants to try to make their travel path as short as possible to optimize that, right? So I used a couple different algorithms to develop this path. We're going to look at the result of just one of them today. But essentially, once I created this path that is optimized in some way to be as short as possible in the 11-dimensional space, I then used this path to reorganize these sound slices in time according to that path. So now I would have a reconstructed version of my audio that has all of the same sound slices as before, but reorganized according to that path. And the premise here, right, is that the slices that are near to each other on this path will be near to each other in the 11-dimensional space, and they'll be near to each other in the 11-dimensional space because their audio analyses are similar. So hopefully, the similarity of those audio analyses will give me the sort of similarity that I'm looking for in this reconstructed audio file. So we'll hear that reconstructed audio file in just a moment. Ooh. But before we do that, I'll orient you to this graph here. So each one of these dots is a sound slice. The two-dimensional space here is the result of a dimensionality reduction algorithm going from the 11-dimensional space as the output of PCA down to 2 dimensions. And I use an algorithm called UMAP to reduce it to 2 dimensions here. So what we're seeing here on the x and y axes, they're not human readable in any way. It's not like one is pitch and one is loudness. We can't look at the points that way. But what we can hope is that the dots that are near to each other, the sound slices that are near to each other, will sound similar to each other. That's sort of the hope of the dimensionality reduction algorithm here. The colors are the result of a clustering algorithm that was done in the 11-dimensional space. So it's just which we hope that it means that the dots that are the same color will be near to each other in that 11-dimensional space, hopefully will sound similar to each other. So it's just another way to sort of peek into that 11-dimensional space, just sort of see like what similarities might be there, even though our brains cannot conceive of 11 dimensions and we're looking at a screen which is only 2 dimensions. So just another way to sort of peek into that space. So the result that we're going to see, the one-dimensional path that I created, was also the result of a UMAP dimensionality reduction algorithm. But instead of asking it to reduce it to 2 dimensions, I asked UMAP to reduce the number of dimensions to 1 dimension. And that's the ordering of sound slices that we're about to hear. So when I press play, we'll see a black line start to zigzag around this space, connecting all of these dots. That's the path that we're hearing unfold. And we'll also see a video excerpt of the performer actually playing that sound slice. So we'll sort of both hear and see that path unfold and see hopefully the similarities that the algorithm was able to identify through this process. So that's the output of the algorithm that it returned to me was that sequence of audio and then accompanying that sequence of video. So the actual piece is much longer than this and has other sections. This is just from one section. The other sections also use the FluCoMa Toolkit and machine learning in various other ways. But for this section, what I ended up doing was I took this about 2 minutes of audio that it returned, and I'd used another algorithm to do a similar thing, to do the same thing, but ended up with a different path, right? And I found sections of those sequences that I liked, and I actually cut those out and used those and reorganized them in time to give the piece, the content of the piece one more pass on my aesthetic judgment before calling it the piece. So that's these two projects that I was going to talk about. Before I pass it over to James, are there any questions about either of those that anybody would like?
So this was a complete sequence that you did, and so the whole thing was played back through the navigation, through the sales.
Yeah.
So it's like, the recording is of the same length.
Yeah, so I actually did, that's a good question. So there's actually, I had 2 minutes of audio per performer, because it was 2 minutes of music, but they recorded them separately.
Oh, okay.
So I had 8 minutes of audio, and that was what I used to do, that's what created all these sound slices. But then, when I did the re-synthesis here, I had an overlap of 4. So it was, the sound slices were 100 milliseconds, but they started 25 milliseconds apart. So it ended up being 2 minutes. What we just saw was 2 minutes. So that was, about 2 minutes. And the overlap of 4 was just an aesthetic choice, just, playing around with it, seeing what would sound nice.